Okay, everybody. So today we have linear programming problem, and it belongs to the very important topic of applied mathematics, optimization technique, or you can say operation research. And optimization technique is not only an important branch of applied mathematics, but it is useful in any branch of science, not only science, economics, management, financial market, whatever we will study, you have to go for optimization technique, operation research. So actually this subject, operation research, developed during the World War II. There is a very good interesting history behind that, and I will talk about that later on. But today I will talk about linear programming problem. So what are the outlines today? I will talk about the introduction, the linear programming model, examples of linear programming problems. I will give you some examples, and how to develop the linear programming models. And lastly, I will talk about graphical solution of LP problems. I will not talk about simplex method in this lecture today, but simplex method I will talk about later on. So mathematical programming is used to find the best or optimal solution to a problem that requires a decision or set of decisions about how best to use a set of limited resources to achieve a set of goal of objectives. So this basically, mathematical programming is basically leads to the best or optimal solution with the resources you have. And what are the steps involved in mathematical programming? Number one, conversion of stated problem into a mathematical model that abstracts all the essential elements of the problem. Number two, exploration of different solutions of the problem. And number three, finding out the most suitable or optimum solution. These are the steps involved in mathematical programming. Now, linear programming requires that all the mathematical functions in the model be linear functions. That is why the name is linear programming. Linear functions, there is no non-linearity. So, we have a now linear programming model now. Let x1, x2, xn be decision variables and z be the objective function or linear function. So this objective function z can be maximized or minimized. Here we have written only maximization, but it can be minimization also. So our target is to maximize or minimize the objective function z, which is equal to c1 x1 plus c2 x2, c3 x3, etc. Where c1, c2, c3, cn are cost of the individuals of those variables, cost of some quantities, and x1 are the decision variables. So cost per unit of x1 is c1. So naturally the total cost will be c1 x1. Similarly, the cost of 1 unit of x2 is c2. So total cost will be c2 x2. So that way, this is your objective function that has to be maximized or minimized. Subject to the following constraints, you have some non-constraints because some restrictions is imposed on the problem. If you have gone for a market to buy something, there is some restrictions of buying something. If you buy fish, meat, whatever, there is a restricted. You cannot buy more than 1 kg. You cannot buy more than 1 to 2 kg, etc. So these are the restrictions imposed on the problems. So these are the restrictions. Constraint means the restrictions imposed. So the constraints may be of this type: a11 x1 plus a12 x2 plus etc. A1 and Xn less than equal to or greater equal to B1. This is the first constraint. Second constraint, A21 X1 plus A22 X2, etc. A2 and Xn less than equal to or greater equal to B2. It can be less than equal to, it can be equal to, equality, it can be greater equal to. So that depends on the problem. And lastly, you have AM1 X1 plus AM2 X2, etc. AMN Xn less than equal to, greater equal to Bm, where Aij, Bi and Cj are given constants. So these are the constraints. So you have n variables and m equations, m constraints. You have n variables. The decision variables are n. Number of n decision variables are n. And also you have non-negativity restrictions, because in real life situations we will talk about some positive values. Positive x1, x2, xn are positive. So this is called the non-negative restrictions. Non-negativity restrictions. So these are the three parts of an LPP model, linear programming model. First is an objective function that is given by equation 1. Number 2, equation 2 is given by the constraints, and number 3 is the non-negativity restrictions. This is number 3. These are the three parts. So a linear programming model can be written in a more efficient notation if you want to write in a matrix notation. So we can write optimize z equal to cx. Optimize means maximize or minimize. So z is the objective function, c is the column vector, is an n component row vector, which is known as the cost or price vector. Here c, bold c, you look at that, it is a n component row vector, which is known as cost or price vector. And the restrictions, that is the constraints, are given by ax less than equal to, greater equal to b. So a is the coefficient matrix, m cross n coefficient matrix, aij. It's a coefficient matrix. And x is the decision variable, or you can say n component column vector. It is a column. You can say decision variable or legitimate variable vector. And b is the m component column vector, which is known as requirement vector, b. This b is the requirement vector. So that's it. And x greater equal to 0. 0 is the null vector. So you have a very compact representation of LPP. Very compact in matrix notation, in vector matrix notation. Okay. So this is your linear programming model. Now I will talk about feasible solution. What is feasible solution and what is optimal solution to LPP? These are the very important terms related to LPP. A set of values of the variables which satisfy all the constraints and all the non-negativity restrictions of variables is known as the feasible solution to the LPP. This is called the feasible solution. So once again I repeat, a set of values of the variables which satisfy all the constraints. It should satisfy all the constraints and all the non-negativities. It might be positive of variables or 0 is known as the feasible solution to the LPP. And what about optimal solution? A feasible solution to LPP which makes the objective function an optimum is known as the optimal solution to the LPP. So optimal solution must be a feasible solution. For all those feasible solution which optimizes the function, objective function is called the optimal solution. So these are the two very important definition of LPP. Now let us have some examples. What is the use of LPP? What are the examples of LPP? First example, a product mix problem. A manufacturer has fixed amounts of different resources such as raw material, labor, and equipment. These resources can be combined to produce any one of several different products. The quantity of the ith resource required to produce one unit of the jth product is known. The decision maker wishes to produce the combination of products that will maximize total income. Obviously, it is a company who has done the job, a product makes problem. So company wants to maximize the total income with the minimum expenditure of his raw material, minimum requirement of raw material, labor cost, and all infrastructure costing. He want to minimize and want to maximize the total profit. That is an example of product mix option. So we can apply LPP in this type of problems. Next, blending problem. A blending problem. Here also we can apply LPP. So what is a blending problems? Blending problems refer to situations in which a number of components or commodities are mixed together to yield one or more products. Like, just for example, steel. A good quality steel can be produced. Tata Steel, just one of the company, it's a renowned company. They can produce a good amount of steel by mixing with other iron ore and some mica, maybe some other raw materials or other minerals they can produce. They can mix up and uh, beauty, greater quality or yielding one or more products or better quality components or commodities can be produced. So this is this type of blending problems. Typically, different commodities are to be purchased. Each commodity has known characteristics and costs. The problem is to determine how much of each commodity should be purchased and blended with the rest so that the characteristics of the mixture lie within specified bounds and the total cost is minimized. So this is called the blending problem. So your LPP can be applied here also. And next is production scheduling problem. A manufacturer knows that he must supply a given number of items of a certain product each month for the next 10 months, and they can be produced either in regular time subject to a maximum each month or in overtime. The cost of producing an item during overtime is greater than during the regular time. Our storage cost is associated with each item not sold at the end of the month. So this is production scheduling problem. So there will be some production unit. You are producing a unit for a month and you can keep them. You need a storage cost, a large amount of storage capacity that will cost. So company has to manage all this. They want to reduce this storage cost, minimizing all this time, regular time, labor cost in this thing also. And lastly, they want to sell these products. So the problem is to determine the production schedule that minimizes sum of production and storage costs. Transportation problem. This is a very beautiful problem. And you have a different topic, actually a chapter in LPP of transportation problem. Suppose a cold drink manufacturing concern. They have some units origin, they have a production, and they have some destinations. So they have to ship the products into that destinations. So they have some origins and some destinations. Suppose you can talk about 7 Up, you can talk about Mirinda, you can talk about Thumbs Up, Pepsi. These are the cold drinks. So there are some manufacturing units, there is some production. So actually cold drinks are manufactured at those origins and there are some destinations. So you have to transport those M units of products to that destination. They have some capacity, they have some requirement. So this is a transportation problem actually. So here also you can apply your linear programming model. I will discuss everything later on. And there is also flow capacity problem. So there are a lot of problems. This is just a example, the some examples. There are some. So flow capacity problems, one or more commodities are flowing from one point to another through a network whose branches have various constraints and flow capacities. The direction of flow in each branch and the capacity of each branch are known. So here also this is a network type problem. So network is a very important concept in optimization. So now I will talk about developing how to develop a LP model. So the variety of situation to which linear programming has been applied ranges from agriculture to zinc smelting. So steps, what are the steps? Number one, determine the objective of the problem and describe it by criterion function in terms of the decision variables. Number two, find out the constraints. Number three, do the analysis which should lead to the selection of values of the decision variables that optimize the criterion function will satisfy all the constraints imposed on that problem. So these are the steps for modeling a LPP. Now let's have a problem and I will develop a LPP. Product mix problem. So look at the example first very carefully. The industrious company produces two products, 1 and 2, product 1 and product 2. Look at the chart also that is given. The raw material requirements, space needed for storage, production rates and selling price for those products are given in table 1. So product 1, what is the storage capacity, storage space, square feet per unit 4, and for 2, 5. Raw material, pound per unit needed 5 for product 1, 3 for product 2. Production rate per units per hour, For 1, 60, that means 60 units per hour. For product 2, 30 units. This information will be given in the problem. And what is the selling price? Dollar per unit. $13 per unit production selling price for unit product 1 and $11 per unit for product 2. So this is the chart given. Now also it is given in the problem, the total amount of raw material available per day for both products is 1575 pound. Okay, that is the total amount of raw material available per day for both products. And the total storage space for all products is 1500 square feet. And a maximum of 7 hours per day can be used for production. So these are the informations given. Now let us formulate the LPP. That is the most important part of LPP, linear programming model. If you can't formulate the problem, you can't solve the problem. So first step is to formulate. That means you have to write the objective function and the constraints. So all products manufacturing are shipped out of the storage area at the end of the day. Therefore, the two products must share the total raw materials, storage space, and the production time. The company wants to determine how many units of each product to produce per day to maximize its total income. That is the objective of the company. That is the objective of the problem. So you have to identify the objective of the problem. The company wants to determine how many units of each product to produce per day to maximize its total income. Now, solution. The company has decided that it wants to maximize its sale income, okay, which depends on the number of units of product 1 and product 2 that it produces. So let, for example, the decision variables x1 you have to assume, and x2 can be the number of units of products 1 and 2 respectively produced per day. Look at the question once again. Okay, so there is not mentioned that what unit produced in per day. So I'm assuming per day x1 units of product 1 and x2 units of product 2 are produced per day. Okay, so these are the decision variables. So what is your objective function? What is the cost per unit? $13 product 1 per unit and $11 per unit for product 2. So for x1 unit, the cost will be 13x1, and for X2 unit, the cost will be 11 X2 for product 2. Okay, so what is the total cost? Total cost will be Z equal 13x1 plus 11x2, and this has to be maximized. So what is your target? What is your objective? Is to maximize this function 13x1 plus 11x2, subject to the constraints on storage space, raw materials, and production time. Go to the chart once again. You have a restricted storage space, raw material, and production rate. So you have to put into the constraints. Let me go to the constraints part. So each unit of product 1 required 4 square feet of storage space, and each unit of product 2 requires 5 square feet of storage space. So go here. Go to the chart. You see 4 square feet per unit, 5 square feet per unit, respectively for product 1 and product 2. So for X1, it will be required, and for X2, what will be required? Let's check. Obviously, for 4x1, for x1 units, we required 4x1 square feet of area, and for x2 units, we required 5x2 square feet of area. So total storage space needed each day is 4x1 plus 5x2, and this space must be less than or equal to the available storage space, that is 1500 square feet. So 4x1 plus 5x2 less than equal to 1500. This is your constraint number 1. This is your constraint 1. Look at the chart. Restricted. You look at that. It is the question. The storage space for all products is 1500 square feet. Your storage space cannot go beyond that capacity. It is restricted capacity. The capacity is 1500. So you have to restrict yourself here. So 4x1 plus 5x2 less than equal to 1500 is the first restriction constraint. Similarly, each unit of product 1 and 2 produced requires 5 and 3 pounds respectively of raw materials. And also you have a, go to the table, raw materials, you have a restriction on raw materials, 1575 pound for both products. So for x1 units, you need 5x1 pound, and for x2 units, you need 3x2 pound raw materials, and that must be less than equal to 1575, because this is the maximum raw material needed. So that must be less than equal to, so hence total 5x1 plus 3x2 pound of raw material is used, and that must be less than equal to 1575. That is the second constraints. Okay, dear students, I hope you understood how to utilize the constraints. This must be less than or equal to. Now there is another constraint, and the last constraint, that is the production rate, 60 units per hour and 30 units per hour for product 2. So this is the, and maximum of 7 hours per day can be used for production. Okay, so for x1 units, it will be, you can carry on the calculation. So product 1 can be produced at the rates of 60 units per hour. Therefore 1 minute or 1 by 60 of an hour to produce 1 unit. Similarly, it requires 1 by 30 of an hour to produce 1 unit of product 2. Clear? So hence for x1 unit, it's gonna be x1 by 60, and for x2 units, it's gonna be x2 by 30 hours. It's required for the daily production. This quantity must be less than or equal to the total production time. What is the total production time? Company has restricted the total production time to 7 hours. So it's gonna be 7. So x1 by 60 plus x2 by 30 less than equal to 7. So this is the third restriction. So look at that. Everything is given in the problem. You have a chart in the problem. You have to write the restrictions according to your problem. So these are the constraints. And finally, your non-negativity restrictions, that is x1 and x2 must be greater or equal to 0. That is your LPP. So your LPP becomes maximize. The linear programming model is maximize z equal to 13x1 plus 11x2 subject to the constraints 4x1 plus 5x2 less than or equal to 1500, 5x1 plus 3x2 less than or equal to 1575, and this is gonna be x1 plus x2. If you simplify, x1 plus 2x2 less than or equal to 420, and x1 x2 greater or equal to 0. This is the non-negativity restriction, this is the constraint, this is the objective function. So this is your mathematical formulation of the LPP or linear programming model. Now I want to solve this. You have two decision variables, so I can use graphical method to solve. How will you use graphical method? I will have two axes actually. I will take two decision variables along the axis x1 and x2, and I will put them in a straight line, because 4x1 plus 5x2 less than or equal to 1500, it is a straight line. So you can draw like this, you can draw like this, and you can draw like this. So if all the regions, so I will draw this. So look at that, it is drawn here. You know how to draw the straight lines taking intercept. This is the straight lines. And why this region is shaded? Actually, you look at that, your first constraint 4x1 plus 5x2 less than or equal to 1500. If you put it, it includes 0 0 origin. It's include origin 0 0. Its arrows will be towards origin. Why? Because if you replace x1 x2 by 0, that's gonna be 0 less than or equal to 1500. So it's true and it satisfies. It satisfies. So its arrows will be directed towards the origin. Similarly, you can check the other constraints that will be towards the origin. If it doesn't satisfy, it will be away from the origin. So there are two ways actually, two options. Either it will satisfy, so they, in that case, the arrows will be directed towards the origin, or it will be away from the origin. After that, you will have a common region. So you will shade the common regions. Okay, you will shade the common region. So this common region will give you the feasible solution or feasible space. And look at the corner points. You have a corner points or extreme points. These are called extreme points or corner points. This will give you the optimal solution actually. This will give you the optimal solution. So look at that. The arrows will be directed towards the origin in this case, and this is the diagram, and you have this feasible region. And after solving, you will get these points, these corner points, 1, 2, you check that you have 4 corner points. You can get these corner points, and these corner points can be substituted in the objective function, and you will get the value of the objective function. You will get the value of the objective function, just like you get the value of the objective function at this dollar, with x1 equal to 270 and x2 equal to 75. One of the corner point will give you the optimal solution. One of the corner point will give you the optimal solution. In that way, you will get the solution graphically. So I will explain another problem. Okay, but before that, I will explain something about the graphical solution. If the objective function happens to be parallel to one of the edges of the feasible region, or any point along its edge between the two extreme points, may be an optimal solution that maximizes the objective function. When this occurs, there is no unique solution, but there is an infinite number of optimal solutions. And the graphical method of solution may be extended to a case in which there are 3 variables. It is very easy to have the graphical solution for 2 variables, but for 3 variables it will be difficult, because that will be 2-dimensional. In this case, each constraint represented by a plane in 3 dimensions, and the feasible region bounded by these planes is called polyhedron. But more than 3 variables, it is not possible. We will go for simplex method. Let's have a problem on graphical solution. I will show you the graphical solution only. Suppose you have maximized z equal to 4x1 plus 7x2 subject to 2x1 plus 5x2 less than equal to 40, and x1 plus x2 less than equal to 11, these are the constant, and x2 greater equal to 4. So x1, 2x1 plus 5x2 less than equal to 40, this will intersect the x1 axis at 20 and x2 axis at 8. Okay, so let's have, yeah, this is 20 and this is 8. Already I have taken two axes, x1, x2. So let's draw the straight line. Yeah, like this. This is the, suppose this is the straight line. And you have x1 plus x2 less than equal to 11. So it will intersect the x1 axis as 11 and x2 axis as 11. So it's here. Let's take a different color. Yeah, 11, and this gonna be 11. Yeah, this is the straight line, another second straight line, and you have x2 greater equal to 4. So x2 equal to 4, that will be parallel to that will be parallel to x1 axis. So it's like this one. Yeah, this is x2 equal to 4 line. So these are the three lines. Okay, now you look at that, x2x1 plus 5x2, if you replace them by 0, let's check whether they include origin or not. So that's gonna be 0 plus 0 less than equal to 40. So it includes origin. It's origin. Yeah, it's towards, arrows will be towards the origin. Okay, you will put the arrows towards the origin. And if x1 plus x2 less than equal to 11, so less than equal to, once again it will towards the origin definitely. So its arrows will be towards the origin. Okay, and x2 greater equal to 4, so it doesn't include origin, it will be away from the origin, so its arrow will be here. It's like here. Okay, so what is the common region? What is the feasible common region, shaded region? This is the shaded common region, and this gonna be the feasible region. So this, you have four extreme points, 1, 2, 3 and 4. Four corner points, A, B, C and D, and I have solved it. So DA gonna be 0, 4, obviously from your graph, and B you can solve it. B is 7, 4, and C is 5, 6, and D gonna be 0, 8. So you have four extreme points or corner points, A, B, C, D, and ABCD is the feasible region. ABCD is the feasible region or the solution region, and your optimal solution will be obtained at these extreme points. So you have to test for ZA, objective function at the point A, you have to substitute ZB, ZC and ZD and check which one is maximum, because it is a maximization problem and that will give you the answer. Similarly, you can go for minimization problem. If you give, if it given by minimum, then that will give you the minimization. Okay, so that is how you can deal with the problems of LPP. You can formulate the LPP model with the constraints, with the objective function and with the non-negativity restrictions. And if it is a two decision variables you have, you go for the solution and find out the graphical solution. Okay, so that is my first lecture today. I will give you second lecture very soon. Thank you all of you.